Hey everyone, I'm James Melvin. Welcome to GPU Mode lecture number 33, GPU Mode going from strength to strength. Thanks for joining in this early or late, depending on your time zone. Well, it is with immense pleasure that I invite you to join me in welcoming Wang Lei. Lei is currently a research intern at the Microsoft Research. He has his works published in conferences such as OSTI, MLSys, ASPLOS, including representative work on BitNet 1.5 bits, TMAC, BitBLAS, Ladder. So he was also awarded the Best Paper Award at the Principles and Practice of Parallel Programming 2024. Today, he will be sharing his recent work on high-performance mixed precision computing with BitBLAS, which is a kernel library, and Ladder, end-to-end compiler. In addition, he will also introduce a new Triton-like programming language called TileLang. With this amazing backdrop, Lei, we are thrilled to hear more from you. Folks, just a bit of housekeeping. If you have any questions, please message them on Zoom. We will pick it up during the talk, else at the end. So Lei, the stage is all yours. Please take it away, mate.
Yeah, so hello everyone, my name is Wang Lei in Chinese. So you can call me Lei. I'm currently a system research intern at Microsoft Research Asia. And I'm excited to share with you our recent work about machine learning compilation. The title of my presentation is Enabling Efficient Low Precision Computing via Hardware-Aware Transformation. And English is my first language, so I'm not a good English speaker. So if I say anything unclear, please feel free to interrupt and ask questions. So I will start by giving some background on mixed precision computing and then move on to the design and some insights of our systems, BitBLAS and Ladder. And after that, I will share some experiment results that we conducted using NVIDIA and AMD GPUs. And finally, I will walk past some Jupyter tutorials about the BitBLAS Ladder, which is end-to-end compiler, and the Triton-like language, TileLang, to help us to write some mixed precision kernels. So let's first get started with some background on mixed precision computing. Nowadays, from a model perspective, numerical precision is gradually shifting toward into a lower bit format. For example, today we have integer 4-bit format or float point 4-bit format. And as we can see, in just 1 week, over 200 new integer 4-bit models can be found added to the Hugging Face. But traditionally, quantization has been used to quantize the model into a lower precision to help us utilize the hardware low precision instructions like tensor codes. But today, this trend has been shifted because as the model become larger, the primary goal of the quantization is to save the memory footprint on devices. For example, take Llama, we have checkpoint size from the about 13 gigabytes to about 100 gigabytes, but we also have to save some. We also have to reserve some memories on the GPU for the activation and the KV cache. So it's very hard for the GPU to hold the entire model. So today we have some techniques named weight-only quantization. Like they only quantize the weight, and we can also get better performance. For example, if we quantize the 1416 into the integer 4-bit, we can save about 3/4 GPU memories. And some research has even pushed the boundaries into the low bit. For example, today we even have 2-bit, ternary bits, and even 1-bit. However, this introduces a new scenario in computing. In quantized ALM, activations are typically in higher bits, for example, 14.16, while the weight are usually in a lower bit format, for example, integer 4-bit or 2-bit. This creates 3 major challenges. The first challenge is that modern hardware and software systems usually doesn't provide such a precision format. For example, LM4 and some new data types like MXFP. This is not supported by I think most of the hardware and software systems. And the second challenge is most of the hardware doesn't support the necessary computer instructions for the mixed precision computing. Although hardware like NVIDIA GPUs is increasingly supporting lower precision. For example, Emperor, we have integer 8 to binary tensor codes. And Blackwell, we have FP4 and even FP6 tensor codes. But they are designed for consistent computation, meaning both input A and B must be in the same data type. This make operations like a floating point 16 multiplied the integer 4-bit become difficult to be mapped into the computation directly, instructions directly. And lastly, the combination of the computation is very is vast, so making it difficult for developers to optimize all of them, because we have to implement all of the combinations for all of the backend. I think it's very hard. Yeah. So to address these challenges, we have some insights. We have made several key observations and have some insights. The first insight is that the memory system can store any data type by converting the custom data type into a fixed weight opaque data blocks, and can be reinterpreted into various other data types on the software side. And the second insight is that most of the custom data type can be losslessly converted into a wider and standard data types. For example, integer 4-bit, we can be losslessly cast into the floating point 16 and the floating point 32 to utilize the hardware existing instruction to perform the computation. So by leveraging this insight, we can enable mixed precision computing hardware with limited instruction support through tensor transformations. Yeah, this is so we want to pick some insight from machine learning compilers. We all know that the machine learning compiler like TVM or Triton it separates the schedule and the compute. The users only need to learn one single Python like DSL, and the compiler can help us to handle the code gen and the optimizations for different hardwares. So can we develop an abstraction like a machine learning compiler? For example, our goal is to propose a general data type representation that can efficiently handle type transformations and the kernel code generation. For example, that user doesn't need to be aware of how the data type be converted into another data type and which instruction they usually perform the computation. They only need to define the computation, and we handle the type transformation and the kernel code generation. However, when we want to do this work, we find that existing machine learning compiler, including the TVM and the Triton, they do not have the good performance even we under a consistent computing. We do not need a dequant. So, for example, in our development process, we evaluate the compiler systems like AMOS and TV and Tensor. They can only reach about 60 to 80 performance of the BitBLAS on the RTX 3090 on with Tensor code. This is mainly due to the challenge with data layouts. We know NVIDIA GPUs are carefully designed so that when the tensor codes are running at peak throughput, each level of memory bandwidth is fully utilized. So if bandwidth isn't used efficiently, they can bottleneck the computation throughput. However, we know optimized memory layout is very hard. That is because each memory layers, they prefer different memory access. For example, the global memory, they expect coalesced access, and the shared memory, they prefer the free band conflict, and the register memory, they should align the memory access with the instructions. For example, for tensor code, the register should fetch the data from the shared memory with such an order. And we usually have a fixed input data layout. For example, the input A must be row major, and the input B must be row major or column major. that makes the optimizing be very hard. So recent NVIDIA had introduced the concept of swiveling. They carefully designed the memory placement to maximize the performance of across different layers. But the strategy is very difficult to implement effectively. For example, if the data is dequant, the swivel rule will be different, and so so this, so this is still a very hard problem. So our insight is that if we want to design abstraction and to achieve high performance, we should consider the data layout. So with this abstraction insights bear in mind, we designed these tensor-centric system abstractions. The first key abstraction is tile type, which is the general data type that we can use to define our own data types. And user can also define convert functions to annotate how this data type like integer 4 can be cast into another data type like integer floating point 16, and we have a tensor abstraction like type tile, which is a tensor, and we also have an abstraction named index map, which annotates the data layout for each tensor, and we also provide for scheduling templates for scheduling primitives like slice, convert, pad, and transform layouts to manipulate the t-tile, to transform a t-tile into another t-tile. So with abstractions and the primitives, we can define a tensor computation in a new paradigm. For example, we can annotate the output data type and the cum data type and each tensor data type, and finally the program will be described as this scratch. Each tensor transformation can be defined within some transform functions, and each transform function are composed with the tensor primitives. And furthermore, at the end-to-end level, for example, a llama model can be finally lowered into a t-tile graph. This allows us to directly manipulate the tensor, and each tensor in the t-tile graph is a t-tile, and this allows us to manipulate the tensor and to transform the tensor across different memory layers and different operators. And these abstractions can enable us to open a new design space for traditional machine learning compilations. For example, what's the base data layout for each t-tile across the t-tile graph, and which instruction should we utilize to perform the computation for the given tensor expression, and when should the dequantization happens? It may happen in the register, and it may happen behind in the global memory to shared memory, and we discussed these topics in our paper that published as this year's OCDI. So you can find some detailed information, and I will have a brief introduction of these concepts. I think the first challenge is to find the right hardware instruction to perform the specific computation. So we first developed a bit near-with instruction matching. For example, we can cast integer 4-bit. For example, we can cast integer 4-bit into floating point 16 or into the floating point 32. And for floating point 16, we have we have several candidates for computation. For example, HMM2 for the CUDA code and HMM2 for the Tensor code. So which instruction should we use to perform the computation? So we have some abstraction for the instruction. For example, we define the flops, the data type, and the computation for each instructions, and we will match the instruction based on its T flops and the data types to determine which instruction we should use. So, but how can we know if dedicated tensor operation can use a specific tensor computer unit? So anyway, we implement a solution a bit accomplished in Plan A4. So essentially, we use the iterator classification method to determine the best way to map a computation to the target instructions. For example, we have the convolution expression. They have 4 spatial loop and 3 reduction loops. And our target, for example, our target instruction, the tensor code, we define there, we have 2 spatial iteration and 1 reduction iteration. How can we map the convolution into the tensor code expression? So we use the iterator-based fuse method to determine deduce the base map rule, and after applying this optimization, we can get a transform to input and weight, and the final and we have a compute kernel that is a tensor code map flow. So I have simple tutorials about these functions. For example, like we can define a convolution expressions, and we can initialize the target. For example, we initialize CUDA arc from the NVIDIA 4019 GPUs, and we can utilize the function that we provided, get a tensorized function and text. After apply this function, after apply this transform function, we can get a tensorized function. If the tensorized function is not known, that is let's say the convolution can be mapped by the target tensor code instructions. And we can see the tensorized function. We have some transformation to the pad and the weight, and we have a code blocks to perform the tensor code-like computation. For example, batch and nk, and finally we have a code block to recover the convolution data layout. I think this is very interesting because with this method, it can enable us to explore if a given custom expression, for example, convolution and stencil, can it be tensorized by target instructions. And as you can see, if we use the convolutions, the final map flow is turns out to be image column. Yeah. So the first major challenge is to optimize data layout. So which is very difficult due to if you want to search the data layout, you can find the search space is very large, and the search space is overlaps with the search space for the computation tile configs, for example, BM, BK, and the BN. And to address this, we developed a method for inferring memory layouts that automatically align with the layout with the hardware instructions. For example, we first have a mathematical expression which is defined in high-level DSL, and we can determine the instructions that we use in each level. For example, the global load, shared load, and compute. And then we can deduce the base layout for the input. We finally have 3 computer kernels. The first two kernels change the layout for the input A and B, and the computer kernels is perfect, maintain perfect memory access. It doesn't have any memory related issues like bank conflict collapse. It just really just sequentially access the data. So we can efficiently reduce the layout search space, but the limitation is that we will introduce two memory transformation kernels. Even though this is an element-wide kernel, it's not very cost. So, but we can eliminate this overhead. To address these layout transformation kernels, we introduce a tile graph approach, which is proposed as a OSDI 23. For example, with element-wise operators, tile graph can help us to fuse the operators at the register level, and if you can, if the 2 operators is in computer-intensive operators, for example, the matmul and the matmul, the tile graph can help us to fuse the kernels in and reuse data in the shared memory. So with this approach, we can propagate our layout across the tile graph. For example, for the metric multiplication, we can propagate the data layout into the last operators, and this operator just need to change the write back address. And if the final operator is a constant weight, we can do some constant folding to apply the data layout. And we also have some tutorials for the tile graph in the Jupyter notebook, and we will discuss it at the final at the end of our talk. So we can deduce the layout, but how can we do layout propagation? And why layout propagation is hard? This is mainly due to three challenges. First, the scale of the problem and the available instructions are often misaligned because the shape of the instructions is kind of fixed value. For example, the tensor code usually is 16 multiplied 16 multiplied 16, but the given compute is unbounded. The MNK can be any value. And the second, there are several other computations outside the core MMA instructions. For example, we can deduce the memory layout for the MMA, but if you want to propagate the layout into the weight, we have several other operators like dequant and image column that we need to handle this case. So to tackle this, we designed a dedicated layout propagation mechanism. We first categorize the layout into three types. The first type is linear transformation. For example, transpose or the swizzling is linear transformation. The second type involves the data compression that even preserve the one-to-one expressions like a dequantization, but we need to account for data compression during the propagation. For example, we have a given data layout that we propagated. If we want to propagate from the weight to the Q weight, the data layout should be transformed like this. And the third type is group-wise scaling, which results in information loss during layout propagation, which we can disrupt further propagation. In this case, propagation should be halted. So BitBLAS has defined the unique set of propagation methods for each of these three types. So this related code can be found at the let me check. So we have the function layout propagation, which implement the method that that you have a layout from the target block to the from the source block to the target block. You can deduce the layout and apply it to the target block. And we will also come across some conflicts with this layout optimization within or between operators. For example, the conflict within operator can consider dequant as gem. We propagate the MMA layout into the weight, which Martin also applied these optimizations, which actually requires a layout transformation or the weight transformation into the weight B. But if we want to maintain the correctness of the program, we also need to apply the same layout transformation to the scale. But I will discuss it at the last slide. The scale is group-wide scaling, which lost some layout transformation, which have missed some information. It's difficult to, or it's impossible to propagate the layout. It's possible to apply a FJK to the S. So if we want to make sure the program is correct, we should apply an inverse data layout into the read stage of the scale. So, which is also, we can also come across some problems between operators. For example, considering inception structure in the ResNet model. For example, the add node, the next of add node is convolution node or the add node. For the convolution node, it uses the tensor codes and it propagates, it prefers the T-tile-A. For the add node, it utilizes the CUDA code and prefers the T-tile-B. There are two different T-tiles. So the add node will write two different tensors to make sure the program is correct. So which will lead to extra memory write back and some extra memory footprint. So to resolve this, we can duplicate the T-tile-A from the left to the right, and we can deduce the inverse data layout to the T-tile-A, and we can fuse this T-tile and fuse into the add. That add node only needs to write back one tensors, and we can have comparable performance with TensorRT, even with you optimize for the NVIDIA GPUs. So we have about 10 performance speed up. So the key challenge is how to construct the inverse layout transformation. So we introduce a automatic differentiation method to address this. So given a specific layout, we constructed the forward syntax tree and define a differential operators for each node in the tree. For example, for this layout, we can construct a syntax tree, and for the float node, node, the differential operators is add. For the float dive, the differential operator is multiply. Then we use the backward propagation with auto differentiation. We can get the inverse data layout. Which we can apply this into the inverse function of scale and the inverse data layout of the T-tile-A. So this layout may be complex, and the final design space revolves around deciding when to apply dequantization. For example, in a dequantized gem, we have three choices to apply the dequantization. If you apply the dequantization in the registers, it will introduce the much more compute overhead and the significant memory access saving, because you can save the shared memory space and the shared memory bandwidth. You can save the global memory space and the global memory bandwidth, because both data in the shared memory and the global memory are integer 4-bit. And in registers, you have to do dequantization. But each time when you fetch into registers, you will do a dequantization. So the dequant cost may be a bit cost. So if you dequantize in the shared memory, you can save the bandwidth and memory footprint of the global memory, but you will also introduce some dequantize overhead. So if you dequantize in the global memory, you won't save any memories, but you can save the dequant overhead, because you only need to dequant once. And sometimes dequantize in the some dequantization like MXLP to floating point 32 is very cost. So this is a trade-off between the memory and memory saving and latencies. So we designed the latency-oriented optimization search policy to deduce where should we put the dequantization. So in the BitBLAS, we can, for example, take a look at the minimal operators. The schedule open memory prefetch with config was represent dequantized in the registers, and the schedule shared memory prefetch with config represent dequantized in the shared memory. And if you want to dequantize in the global memory, we have we just start another kernel to perform the dequantization. And based on these abstractions and optimizations, we provided two different systems. The first system is Ladder, which is used for end-to-end compilation. It's an end-to-end compiler. It takes titles. It takes only file as the input, and if you have dequant linear, we will make custom operators in PyTorch and export to an Onyx file. And we take the Onyx file into input and apply a lot of optimizations to generate efficient executables for different devices. And I also provided tutorials for the compiler later. And the code of Ladder is at this branch in the BitBLAS. So the usage is we can import Ladder, and we can take an Onyx file with input. I use Llama 16 billion one single layer as example. I also have a video. In Auto, we have 47 operators, and we will explore how to fuse the operators. For example, we will try to explore, for example, the cast, min, add, and multiple cast node, three operators. We will try to explore whether these two operators can be fused, and can fuse these two operators, can get a better performance. If can, we can create a fused group of these two operators. Well, we also can explore how two consecutive math-mode operators can be fused together. As you can see, to fine-tune a Llama model, we take about 4 and 5. We take about 5 minutes, and the performance is very impressive. And I will share some experiment results in the experiment section. And the second system is BitBLAS, which is the runtime kernel library as an operator. You can see we have worked hard to provide a very simple API that abstracts away the tensor the auto-tensorization, layout propagation, and the type conversions. Now this library has been used in efficient QAT, AutoGPQ, and VLM, and we also help the BitNet team to deploy the models. And I also have some tutorials about BitBLAS in the following Jupyter Notebook sections. And I also want to share about some optimization tricks for in the BitBLAS for mixed precision computing. The first trick is fast precision conversion. For example, the process of converting an integer 4-bit into a floating point 16-bit in a standard dequantized flow, 8 integer 4-bit are compressed into a integer 32 data type. In the kernel, we use bit shifting and bitwise operation to extract each integer 4-bit as integer 32-bit. And finally, we use hardware instructions, the type converting instruction, to convert the integer 32 into a 4.16. This approach has some, however, this approach has some limitations. It lacks vectorizations. Each instruction can only dequant one value at one time, and the certain type and the type convert instructions sometimes hardware doesn't provide this data convert instruction. For example, if we want to dequant a 14.8 to a 14.16 on A100 on A100 GPUs, it cannot be applied because A100 doesn't have the type converted instructions in the from the 4.8 to 4.16. And so to address this issue, we developed the fast dequanter techniques, which support conversion such as integer 4-bit, 8-bit, 2-bit, or 1-bit to floating point 8-bit to or integer 8-bit or floating point 16-bit. We also provide the vectorized dequantization, for example, from floating point 8 to floating point 16. So in the BitBLAS, if you want to enable the kernel tuning, this is a simple example of how to generate the efficient CUDA code at BitBLAS. The code snap is from the quick start section at the BitBLAS repository. Like you can define the MMK and AW type, accumulate data type, all data type, and define the group size. If we have scaling and we have zeros, either zeros, quantize zeros, or rescaling zeros, and we then can get efficient CUDA code. So let me start from a very simple case. The AW type is 4.16, and the W type and the W data type is uint4. And if we disable the fast decoding, we can get the generated CUDA source like below. As you can see, the dequantized section in the this is the dequantized part. It use some logic operator to shift the data into an integer 4-bit and use an AND logic AND to extract the data into an integer 32 and use the hardware type converter instruction to convert the data type. And if we apply the fast decoding, then we can get this CUDA code. As you can see in this CUDA code, the dequantized slot was warped into a device function, and in one device function, it dequantized eight elements instead of one element. And the dequantized function can be seen at there. This is the dequantized function. You use some fancy NVIDIA GPU instruction, some PDX to apply the high performance type convert. And this is very important for data center GPUs. And when the bit becomes lower, 2 bit or even 1 bit, the dequant overhead will be more cost. So I can see in the A100 GPUs, if we don't apply the dequantization or the fast decoding, we can only get about 3 across speed up for this case. And if we apply fast dequantization, we can get a better performance.
Lei, we just have one question here from Mobicham. How much faster is the fast decoding mode compared to the simple shift and bitwise op?
Yeah, you can see in this. So if you simply do some combination like floating point 16 multiply the integer 4-bit, this is a very common and simple case. In the game cards like 4090 or the 3090, it may not be very different between with or without applying the fast dequantization, but it's very important. But even with a game card, if you push the boundaries, like push the bits into a 2-bit or 1-bit, or even bitnet with the integer 8 multiply the integer 2, or with integer 1, the dequantization will be cost. So if you want, so in your case, if you apply the floating point, if you want to generate high performance CUDA code for the floating point 16, multiply the integer 2-bit, you need to apply the fast dequantization because the dequantized cost will be considerable as my experience. But even but if you want to optimize your program on the A100 or the H100 GPUs, even with the floating point 16 multiply the integer 4, you have to apply the fast dequantization. Otherwise, you won't get the theoretical speed up. The theoretical speed up, yeah. But this only happens when the kernel is small. Is memory intensive operators. For example, small shape gem or the GemV. But if the kernel is computer bound, you won't. It doesn't matter, I think.
So we have one more question that we'll take. Andre is asking, will BitBLAS fast decont work only on Ampere plus GPUs?
No, actually, we enable it on every GPUs because applying fast dequantization will be always better than doesn't apply it. Yeah. And I can share you some of the some of the code about the fast dequantization. We have some C++ tests for dequantization, like integer to 4 to 1 bit to floating point 16, and to integers. Um, I hope this can help you to optimize your problem. And okay, so the next question is how to apply fast and efficient kernel code generation. When I build a kernel library, I found it very hard and challenging because the shape of the large language models is dynamic. So generating code for dynamic shape remains a difficult problem in machine learning compilations. So, but fortunately, in large language models, only one dimension is dynamic. To handle this, we generate code for different segments of the dimension m, and for each specific m, we search for the base tile configurations and store the results on the database to avoid redundant tuning. This allows us to dispatch each segment to the optimal kernel without repeating the optimizing process. For example, we have I think I should first introduce the static shape tuning in BitBLAS. Like we implement and improve the one tools of the OSDI 22 roller, which is the white box kernel tuning for given tensor expressions. For example, we can first import BitBLAS, then we can define a computation like element-wise add. This is element-wise tensor expressions, and we can get the tensor expressions from DSL, like it's a multiply 1, and we can initialize the CUDA target, and the CUDA target has so many hardware informations. For example, the shared memory capacity, and the warp size, and the L2 cache size, and the transaction size, and even the bandwidth, and the instructions is supported. And we can use the policy to, and we can use this hardware information to help us to generate a high performance search space. For example, we want to top 20 scheduled candidates. Then we can, for example, we get this 20 iterations, and we then BitBLAS will apply all of them and select the best one. For example, in the base schedule, we can find the schedule template of the schedule result of the computation, and then we can get the CUDA code of the element-wise add. Right? We can see this is a high performance element-wise add kernel. And if you want to utilize tensor codes, for example, we can define a matrix multiplication computation, and utilize the get tensorized function tags. We can utilize tensor code. You can see we can recommend 20 high performance kernel candidates for each shape, and after applying and build, we can get a kernel that utilize the tensor codes. For example, we have this for improved L2 cache locality, and we have high performance PTX to load the data, and we have the MMA to perform the computation and write back the tensor. But this is for static shape, right? So if for the dynamic shape, okay. So if for the dynamic shape, dynamic shape is hard because for different shape, you must dispatch different kernels. So in BitBLAS, we utilize the functions, we utilize the methods, like you can see the dynamic range for the input. For example, we set the default value to 1 to 256. And if we do not apply hardware tuning, for example, we set the enable tuning to false, we will get a default schedule for every shape, and we can see the kernel is like this. For every shape, we use the same kernel, and if we are applying hardware tuning, we will tune every shape. We will tune one tile config for m equal to 1 for one tile config for m equal to 16, and finally we can get the function like dispatch function like this. For example, in the m equal to 1, we utilize the CUDA code like SMIT. For the shape between the 16 to 32, we use different tile configurations and different kernels. So and we also have database to avoid duplicated tuning for different shapes. So this is our solution to dynamic shape. But this is a bit trick. Like for example, if the shape is 2055, I think utilize this kernel will be better. But we dispatch to the m equal to 128. So they are the tricks for the fast dequantization. So let's first check out the performance of the end-to-end compiler later. In our publications, we evaluate these systems on 4 devices. For example, the paper, we evaluated our systems on the V100 GPU, on the A100 GPU, A100 GPUs, and even game card A1600, and even on the AMD GPUs, and my 250. And because we provide the type abstraction and open new design space for the compilers, we we select 6 models from the LLM to the classic model like resonate and shuffle-late, and accuracy average we can get about 10% speed up over the welder, and even over the Tensor RT, and we can support a lot of new data precisions. Like we can also support bitnate. And from the kernel and from the operator side, BitBLAS can outperform vendor and developer handwriting kernels like Marlin. And often it offers much more greater flexibility in supporting a wider range of data formats. And even with a consistent data format like the floating point 16 tensor code or the integer 8 tensor codes, our system can also have comparable performance, or even have, in some cases, have better performance in cuBLAS and cuDLAS. And we also can have about 60 to 40 speed up than the BLAS on the AMD GPUs. I think that is very fantastic. And finally, we share performance scale up with Llama 60 billion. So we scale the activation data from the floating point 16 to the integer 4-bit, and we scale the weight from the integer 8-bit to integer 2-bit, or to integer 1-bit. And we evaluate our this configuration on the Llama 16, Llama 70 billion models, just 1 layers. And we select 2 configurations, and the batch size 1 sequenceless 1 for the decode stage, and the batch size 1 sequenceless 4096 for the prefill stage. And you can see the because the decode stage is memory intensive, the speed up come across the memory bandwidth saving if we utilize lower precision data formats like for weight. Because the prefill is compute intensive, I think the speed up is relevant to the activation data type, because if your activation become lower, we can utilize a more efficient computing instructions. For example, if we use integer integer 8-bit to the activation, we can utilize integer 8 tensor codes. If we want to, if we utilize integer 4-bit data type, we can utilize 4-bit tensor codes. So this makes sense. And the summary, and our work have introduced several key innovations into improved tensor scheduling for machine learning compilers. And the first, we propose universal tensor abstractions and schedule primitives, which allows machine learning compilers to explore more flexible and optimize tensor scheduling strategies. This is complemented by our hardware-aligned memory layout propagation strategy, which automates memory layout inference, including manual overhead and improving performance across different hardware platforms. We also developed bit-nearest instruction-aligned tensorization strategy to auto-deduce which instruction should we use to perform the computation. And additionally, we designed later BitBLAS and these two systems to help us to improve for end-to-end optimization and kernel optimization. But we also have a lot of challenges. The community has highlighted that kernel compilation still takes too long. I can see even we can tune a static kernel, we can generate a high-performance kernel for static shape in seconds. But if we for dynamic shape, we should tune about 100 kernels for AM. This is very costly. Even we have database, this may lead to some uncomfortable user experience. And furthermore, the BitBLAS implementation is schedule-based, like make it hard for developers to extend BitBLAS. And I want to share with you some of the code of the BitBLAS. For example, BitBLAS first defined example. BitBLAS first defined operators. OPs general. I can see we also support flash attention and matrix multiplication. Currently, we describe the matrix multiplication or the dequantize in a single file. It just represents the computation logic of the expression. It doesn't contain any schedule or the CUDA code or the CUDA related informations. And then we get the computation. And apply some schedule primitives, like for example, to utilize tensor code, to utilize the fast dequantization, and to schedule to bind the thread. This is very complicated and make it hard for developers or even us to extend. And it's also hard to introduce some very hacky schedule like StreamK or speed K. So I was gonna to introduce some the TileLang language. I can see in the BitBLAS we recently pushed some TileLang language related code. For example, the mathematical expression, the mathematical operators. We have a backend named the TileLang language, and in the TileLang language we have the TileLang, right? For example, we can directly write the dequantized kernel in a very simple way. For example, the general dequantized matrix multiplication, and we consider all of the case within one kernel. Like if you have scale, you have Q0s, if you have LAT, and we have some if else configuration to control whether we should enable some optimizations, and we will have a simplified path to remove the redundant AST or even the function argument from the code. Like this is very simple. You can see we can copy A to shared memory and copy B to the shared memory, and we can apply, for example, faster dequantization if we want to enable fast dequantization, or we just use normal dequantization. Then we apply GM and write back to the kernel. And I think it's very clean, right? Besides, unlike this schedule template. But this schedule template is very powerful. It's also very powerful if you are familiar with the TBM. So I have a tile language tutorial to introduce the tile language, but this is not officially released. But you can use tile language to you can import BitBLAS to utilize the tile language. Currently, put the tile language. For example, you can use these three import statement to import tile language. For example, if you want to define a gem multiple multiplication operators, you can use. It's very simple. We can define shared memory and local fragment, and we have a context about how many threads we are used and how many blocks we are launched. And we will automatically map the thread into the computation. The generated code is quite clean.
Just a sec, Lei, just a sec. Abdul, could you mute your mic, please?
All right.
Thank you. Yeah, sorry, Lei.
So it can also be inferenced from a touch tensor. And we also provide some fancy features in Triton, like we can annotate the data layout to apply some suite or pad. For example, the direct data layout may not be very perfect. If you want to apply your own data layout, you can write layout transform functions. You can help you to transform the shared memory layout. And you can also improve the L2 locality with a very simple syntax, and you can also control the pipeline. For example, if you want to apply the pipeline stage, and if you don't want to use t dot copy, you can also use t in parallel to automatically map the tensor to automatically write your own copy statements, and we will automatically inference the vectorization and the thread mapping to, based on the context that we utilize in this content. And also, if you want to implement your own dequantizations, like for example, you can write your own dequantization here. You just copy the quantize the B from the global memory into the shared memory, and you can copy the dequantized memory from the shared memory to the local memory to the registers, and apply dequantization into registers, and apply gem and apply the MMA tensor code from the register and the shared memory. And this might be a perfect schedule. You can, if you are perfect, if you have some expertise in the dequantization or write CUDA kernel, you can also write some PyCUDA code. This code will be translated into the CUDA. So you can write your own code here. We also have flash attention support for this case. Like we can use these primitives to define a flash attention. And all of these tutorials can be found at the BitBLAS repositories at the tutorial section. And feel free to reach and ask some questions about these sections. And thank you for all your attention. If you'd like to learn more or reproduce our results, you can find the relevant code and resources in our GitHub at the link we provided. And for more information, including some technical details for the optimizations, feel free to scan the QR code. And once again, thank you for watching. And also, I'm looking for a machine learning system PhD positions. So if you have any chance, please reach me out. So I'm happy to take any questions. Thank you.
Yeah, thanks, Lei. Thanks, Lei, for this wonderful presentation. I mean, it's been like intense and fantastic work on BitBLAS. TileLang is definitely very interesting. And folks, please reach out to Lei on Discord. He goes by LEI on Discord. So all these slides and the video will be there on the usual channels, I suppose you know. And for anyone who's new, we have a GPU mode YouTube channel, as well as there's a GitHub repository where all the slides would be posted. So yeah, please do connect with Lei. Lei, once again, fantastic stuff. It went really smooth. And also thanks to all the people who joined. I know it's been early, late, depending on the time zone. And if you have any other questions, please ask on the chat right now. Or you could, go ahead and connect with Lei offline. So, yeah.
Yeah, because yeah, this is supported by Microsoft, I think, because I did work at Microsoft during the internship at Microsoft, so the repository was put in the Microsoft organization.
Yeah.
Yeah, but I'm the main developers.
Yes, he's the chief maintainer. You can see his GitHub profile. It's all completely laid out with green. So he's been like absolutely neck deep into this, or perhaps drowned into BitBLAS. I can see. So yeah, cool. We just see if there are any more questions. If not, I think we'll call it curtains then. All right. Okay, folks. Thanks for joining. I think we're done. So yeah, thanks, Lei. Have a good week.
Yeah,
We have wonderful talks coming up next week and the week after. I think the next week is by Moby Cham. So yeah, tune in again. So yeah, goodbye and have a good weekend. Bye bye.
Bye.